Please welcome to the stage, Jean-Paul Biberian.
Thank you. Everybody's here? Well, almost. Anyway, I'm going to talk today about something that's never been done before, I think. And this work has been done in collaboration with Patrick Jacoutan and Eric Marmiroli from Marseille, France. The question we had, what happens if we have a variable magnetic field on alloys, nickel-based alloys? As you know, alloys is nickel is ferromagnetic up to 358 degrees centigrade. So above that, it's lost its magnetism. So what's happening between these two temperatures? So we have worked for 7 years on that, kind of a secret kind of experiment. Nobody knew about it because it was so crazy. And after that, after so many years, we found some experiments that show some reproducibility. The experiments have been done under vacuum and under hydrogen also. We need to do some more work on deuterium, but it's not been done yet. Normal behavior of heating device, any system you have, the temperature is easy to get at the beginning, and then it levels off. It's harder and harder. So that makes sense, it's very normal. Now, what we have observed is something like this. Below the Curie temperature, we are below the normal temperature, and above the Curie temperature, we are above this temperature. So there's anomalous behavior there. We have done two setups. I'll show you the first one, which is really crude. It's two wheels made of wood with magnets on top, so that you have north-south, north-south, north-south between the two magnets, two rolls of wood. And so we can put a test tube in it, we can put powders, we can heat it up, and we can rotate and change the speed of rotation. This is one of those. This is a Pyrex tube. And at the end, we have wrapped a Cantal wire so that we can heat up the tube to change the temperature. There is a K-type thermocouple in the middle to measure the temperature. So to start with, we decided to, didn't tell you the magnetic field is pretty high, about 0.3 to 0.4 Tesla. And the frequency of rotation is 0.5 to 7.2 Hertz. We can have vacuum pump, we can enter gas. We can do calibration in vacuum and under gas also. Let's see. So we do first a blank with an empty tube at different frequencies. And then we put the powder and look at the differences. We go by steps, and we wait for stabilization of everything, of the temperature, by step to 5 or 10 watts, depends. We wait. Stabilization takes 30 to 60 minutes, depends. So the first choice experiment we had, we wanted something that was highly loaded with hydrogen. So we took a nickel metal hydride battery, charged it up to maximum, and then cut it in two and to get the grid, the metal grid that's inside. As you know, the first experiment always works. The other ones are more difficult to reproduce. So the first one worked. Then when we try to do that again, when you cut it, you make a short and you discharge your battery immediately. So we tried, after that, there's a list of materials we tried. You can look at this, I don't need to read it. We tried all kind of crazy things to have something loaded with hydrogen. Okay, this is the curve. You can see that one curve. And this is with lanthanum and lithium aluminum. We tried so many different things. And then we show temperature jump here when we used nickel nanopowders, 20 nanometers in diameters. When we used the nickel nanopowder as it is, there was no temperature jump, because something happens that you have all these nanoparticles don't like to be separated too much, and they agglomerate, and you lose the nanometer dimension. So what we did, we mixed it in a cement so that they will be dispersed, and they will not agglomerate again. And that's how we got this jump. You see a jump of almost 50 degrees when you reach that temperature. Another one here with, you can see the jump. I blew up here, you can see the jump again. Influence of the frequency. There is the temperature is still the same. It's always at the Curie temperature of nickel that's happening. Because of the speed, you have some cooling effect to the ventilation due to the rotating flange, the two rotating wheels. So that cools down a little bit, so changes the power. Now you can see a blow up of the temperature, the frequency effect. But again, it's always at the same temperature. This is one which shows a very precise jump. I mean, at one point we go I try to see exactly what the best jump is, like kind of. And here a detail, you see, within 1 watt, we have a jump of 40 degrees. I mean, it's impressive, you know, that's not normal. Now we went to a better equipment. We have a second setup. These are metal. It's a much better construction. Now we have 2 arms with altogether 72 very strong magnets. And the stack of 3 on each side. There are 6 of them. I mean, altogether 72. And this can rotate with a motor again. Well, here it is. You can enter same way a test tube so we change it to quartz because we want it to go to high temperature, and Pyrex will melt if we go too high in temperature. Same thing, quartz test tube with a heating resistor around. And the setup to put it exactly always at the same dimension, same position. We can measure the pressure inside. Okay. 2 arms rotate, so we can change the speed also. And we go from 0.16 to 6 Hertz. In terms of indication, the power, I mean, it's the power of the motor doesn't depend if there is a test tube or no test tube in it, with powder or no powder. But for indication for you to understand, it's about 4 to 36 watts, depending on the rotational speed. It's a DC motor. So again, we tried a list of things. Even you can even see gadolinium, because gadolinium has a Curie temperature which is very low, almost room temperature. So it's not very easy to work at room temperature anyway. But we tried, not very successfully. We tried different powders. After 7 years, we have a better understanding of what's actually happening. We not do the mistakes we have done before. Again, we have the same effect. You can see the jump in temperature about 358 degrees C. Here, I can calculate the cooling effect and the heating effect with temperature, with speed. So, I mean, I cannot kind of understand excess heat. I cannot understand excess cold. I mean, this is really a challenge for my mind, you know. But we've seen it again and again and again. So this is good for theoreticians. I mean, I don't want to spend time on that. I do the experiments. You guys do the theory. Now, once I mean, when you take nickel, at first, I mean, hydrogen will not go inside because, you know, it's endothermic reaction. So you have to go to higher temperature, then you can put the hydrogen inside, and when it is inside, then you don't have the problem because it stays inside. It doesn't go out. You need to, there's no driving force to take it out of there. In order to get it out, you need to put oxygen or something. Then it will go out. So what we have done, once the powder has been filled with hydrogen, we looked at the effect of frequency on the temperature at room temperature. I mean, there's no heating at all, so there's no errors. So we start from room temperature, and we go, and as you can see, at 3 hertz, we have an increase of temperature of 42 degrees. I mean, it's amazingly high, because if you do the same thing without hydrogen, there's almost no effect. I mean, maybe 2 degrees increase in temperature due to eddy currents, you know, but this is very low. So it's amazing. So discussion. So we have observed cooling, a lot of cooling, and then heating was harder to get to, but we observed it. Always at the Curie temperature. The hydrogen is very important. The frequency is important. The particle size is important. According to, no, I mean, size it matters, but here smaller is better. That's other situation was the opposite. It cannot be magnetocaloric or something like that. It doesn't make sense to have that because there's no cycle actually. It cannot be explained by the heating effect. Also, it's too small. You need to have hydrogen and nanoparticles of nickel. A nano, I mean, I have to be a bit more prudent about that. We could be a bit bigger than nano, but I think one of the dimensions has to be small. I don't know which one, I mean thickness. We have taken, in the last experiments, we started with nickel foils, and when I cut it in dimension like 1 or 2 square millimeters, it was working very well. If it was bigger, it didn't work. So there's some effect of the size. So we have discovered a new effect on nickel-based materials. And a good thing is it works with pure nickel. There's a lot more work to be done, and there's certainly some applications, but we are really in a new field, and I think more people will be interested in maybe do some more experiments. There are certainly potential applications. I was thinking about going to Venus, because it's very hot there. We can cool down a little bit with this apparatus. This is for NASA if they want to do some exploration of Venus and not only Mars. Okay, thank you very much for your attention.
Jean-Paul, have you measured the power that you deliver to the motor to determine whether or not the rotational energy is being converted to your sample?
Yeah, that's why I showed at one point the power to the motors. And there's no difference. I mean, you can measure the difference between the thing spinning empty and the one with the powder or with the loaded. There's no difference. It's not that. It's not due to the some kind of effect like that. Yes, we checked that. Yes, obviously. Yeah. No, there's no problem. There's no effect. I just still don't understand why it's happening, but it deserves more work because variable magnetic fields. I mean, we found a solution to do variable magnetic fields without perturbing the heat. With coils we influence, we have heat in addition. Here we don't have that problem. Yes?
I don't understand why you say you don't have any magnetocaloric effect, because there is no cycle. But there is a cycle. Each time the field is reversed, you get some magnetocaloric cycling.
Good. It's been more complicated than that to do that. But if you look at the curve I showed you, which shows the peak at 42 degrees, at 3 hertz, it's only heating. It's not even cooling there. So, I mean, it's more complicated than cooling. There's both heating and cooling. So it's very, I mean, we are in a field where we're just starting after all these years.
All right, we have time for one more question.
Hi, Mike Hallam, professor. Is an electromagnet instead of fixed rotating magnets on a motor? You just didn't think you could get the Tesla field out of it to do the experiment, or did you try this already?
No, we didn't try it. I mean, that's probably something we should do because the fact that we have rotation, there are two things. I mean, the frequency is not enough because the time the magnet stays on top of the tube is shorter and shorter. So it's not exactly like doing, we are changing two things at the same time, both the frequency and the time the magnet is on top of the powder. So if we use coils, it'll be better. But coils are more complicated because then you have a heating effect of the coils. You have to take into account, but it's feasible, yeah. And you have, if you want to have very high, intense magnetic fields, then you need, I don't want to go to supraconductors, but good device. It is feasible. We have to work on that in the future, certainly.
Thank you very much.
Thank you very much.